So in the last section, we looked at mostly calorimetry, Q equals Cm delta T, and we'll visit some items today that deal with mostly phase changes, solids to liquids, liquids to gases, so forth. We can talk in terms of a couple different things. One, we'll look at heating and cooling curves. So here is temperature versus heat. Heat could be in heat could be in joules or kilojoules, so forth. Doesn't really matter what the unit is, but it's interesting here. So we have a solid that is heating up, and when I say heating up, heat is being added and the temperature of that solid is going to increase. When that solid reaches its point where it can start melting, it will melt. And during that process of melting, its temperature no longer changes, but it's still adding heat. So where is all that heat going? It's going towards breaking all those intermolecular forces that are holding the solid as a solid. Once all those have been broken, then it's a liquid, and that liquid will additionally add heat, and it'll also add temperature. Then, when it reaches its boiling point or vaporization point, it will stop increasing temperature, but it'll still increase in heat. And again, all that heat is going towards breaking all the intermolecular forces that hold the liquid together and not allow it to become a gas. And then, and only at that point, will the temperature start to increase again. So if you go boil water, so this doesn't, it's not necessarily a heating and cooling curve of water, but if it was, that temperature for the boiling would be 100 degrees Celsius, and the temperature for the freezing would be 0 degrees, or melting would be 0 degrees Celsius. And so if you're boiling water, doesn't matter how much heat you provide, it's not going to get any hotter than 100 degrees Celsius. Now this is all taking into account that this is at standard temperature and pressure. If we were at different conditions, environmental conditions, then it might have an impact on those temperatures that boils or melts or whatever other phase changes you want to talk about. There's some other phase changes that I can't show on this graph, and that would be sublimation, deposition, solids directly to gases, or gases directly to solids. Okay? With those ideas, we can talk in terms of the same heats that we talked about in calorimetry, but we're going to use a delta still, but we have an H there, and for us we'll call that heat. We'll have another term that we'll call that H a little bit later. I'll introduce it now. It's called enthalpy, but we can call it heat right now. So change in heat, and VAP is vaporization. So that would be specifically if you had a liquid go into a gas, but it'll be the same identical number, just opposite sign if it's condensation. So you're not gonna find it in a textbook delta H vaporization and a delta H condensation. They'll just give you one of those values. Vaporization is typically the one they use, and you just have to know, are you talking about the liquid to a gas or gas to a liquid? If you're talking about liquid to a gas, it's a positive. It has to absorb energy. And if I move this up just a little bit, you can see that as you go left to right on the x-axis, you're adding heat. You're adding heat energy. If you're going with condensation, gas to liquid, it's going to be a negative value. Same number. And so we can talk in terms of heat of vaporization. We can also talk of heat of fusion. Technically, fusion would be a liquid going to a solid, fusing, but we could also use that exact same number with changing a sign to go from solid to liquid, which would be melting. So nowhere in any textbook, I don't think you're going to be able to find a molar heat of melting. They just typically say it's the molar heat of fusion. This is a good opportunity to talk about supercooling. We're not going to have any test questions on supercooling, but it's an interesting idea here. So if you rapidly cool a material, it could actually get below its freezing point and still look and appear to be a liquid. It just takes a little bit of time for all that rearrangement to occur with all the particles so that the intermolecular forces can all work to solidify that substance. Graphically, you'd have something that kind of looked like that. So freezing point's mentioned, but as you can see, there's temperatures that are below the freezing point where it's still in the mix of a liquid. You might see it as kind of a slushy kind of item. Okay, so a couple questions we're going to get to eventually. How does pressure and temperature affect phase changes? So we're going to use a phase diagram. So I'm just going to jump into a phase diagram here. So this is not drawn to scale, but this will allow us to be able to look at some things here. I'm going to make this just a smidge smaller here so we can kind of get that to all fit in. Okay, so phase change of water. Most phase changes, phase diagrams, by the way, are not going to look like water's phase diagram. They're going to look like this. And the difference between the one I just drew and the one that's up here is that the line, whoops, the line that appears right here between solids and liquids for water is negatively sloped. Now, again, people draw this not to scale so they can emphasize this negative slope. Most other substances, or all other substances I can think of, have a positive slope between the solid and the liquid. Now, of course, we do have gas down here. So we're going to be able to use this to interplay how pressures and temperatures, pressures on the y-axis, temperatures on the x-axis, how they interplay. So typically we are at 1 atmosphere. Even in Pittsburgh, we'll probably be close to 1 atmosphere, and it does change all the time. But at 1 atmosphere, you would have on the x-axis that goes down to 0 degrees Celsius and 100 degrees Celsius. So if you want to go from a solid to a liquid at 1 atmosphere, for water, it would melt at 0 degrees Celsius. What would happen then if you had a different pressure? Well, if the pressure wasn't at 1 atmosphere, like maybe, well, let's talk about boiling. So maybe if you were able to create a more pressurized system, by the way, a pressure cooker works like that. Maybe you're at this pressure. So now a liquid going to a gas now would boil at that temperature. I don't know what that number is, but it's way hotter than 100 degrees Celsius. So that's really effective if you're trying to kill bacteria, yeast, so forth. And a pressure cooker would be able to do that. On top of that, you'd be able to cook your food much faster. There's also, not the one you have at home, but dishwashers that you might see in a restaurant would work like that. They pressurize the water so it boils at a much higher temperature. Another scenario. if you went up to the top of Mount Everest. The top of Mount Everest, the pressure is much lower. There's no increments on here, so we're not really sure where this number would be on this graph, but let's just say it was there. So water would boil at that temperature. And again, there's no increments on here, so I can't tell you what that number is going to be specifically. And also the pressure, just like anywhere else, atmospheric pressure changes all the time. But at the top of Mount Everest, now you're boiling water at a much lower temperature. So if you stuck your hand in that water, it's not going to be as hot as what you anticipated with boiling water. So that's kind of an interesting idea. And then we could also, ice skating actually works only partially in this. The phenomenon of ice skating is only partial because of this. There's more to it than this. But if you were going to look at an ice skate, it's actually has it doesn't have a flat bottom. Now I super exaggerated that skate blade, but you're actually on two edges, those two outside edges of the skate blade, and they're pushing down tremendously all the weight. Usually you're on one skate at a time. All that weight is pushing down on the ice. So it's creating lots of pressure. I don't know what that pressure would be, but let's put it up here. So normally ice melts at 0 degrees Celsius, normal, but now maybe you're at that pressure. So now what you thought was ice is now liquid water. So it turns out that while your ice skate blade is on that ice, there's a little tiny layer of water that you've just developed by that pressure change that now lets you glide perfectly right over the ice. Then as soon as your skate blade leaves, then you return to the 1 atmosphere and it's going to re-solidify. So that's kind of interesting. Now, of course, there's a little more physics to it than that, but at least we can relate this to a phase diagram. Let's see. So I think we've already answered the Mount Everest question. We've already mentioned the ice skating question. Draw the correct approximation for the phase diagram of CO2. So this is interesting. Why? Because carbon dioxide sublimes at normal conditions. That means it doesn't get to pass through the liquid phase. So on my phase diagram of water, 1 atmosphere was up here. So at 1 atmosphere, you could see solids. You've seen ice. You've seen liquid water. And you can't see it, but you know it's there. There's gaseous water. Well, carbon dioxide, the 1 atmosphere has to be somewhere below, we'll call this the triple point. I didn't define that up to this point, but you still have that solid, you still have that liquid, you still have that gas component, but the 1 atmosphere has to be anywhere for you below the triple point. Okay? And by the way, remember I was telling you that this division between solids and liquids for almost every other compound is a positive slope. Water, negative slope. And again, not drawn to scale. Okay, and our last question is, I'm going to make this a little bigger again. Okay, is a previous AP question. So there is a combustion reaction here. And this combustion reaction is taking place in that, I guess you can call it a little alcohol burner, okay? And the energy that is happening with that, that's, we'll call it created right now, but we don't want to violate the law of conservation of mass, but that energy is being transferred now into the beaker that has some water in it above it. Okay, So student heats a sample water by burning some of the C3H7OH propanol. The alcohol burner uses a wick to draw liquid up. That's not so important for us. The mass of the propanol is determined by weighing the burner before and after. Okay, so we have the mass of the combusted propanol. We have how much water was in the beaker. We have our two temperatures, and we have the specific heat of water. So I think with these things, I have no idea what the questions are going to be, but with those items, we could figure out how much energy the water absorbed. And if we know that, we also know how much energy the propanol burning, that system, released. So calculate the magnitude of heat energy, this time in kilojoules. So when we get this answer for Q, it's going to be in joules, but we're going to change it to kilojoules. Assume that the energy released from the combustion is completely transferred to the water. That's not actually going to be the case. You would love if all the energy transfers just there, but it's going to transfer to all the other surroundings also. So we have the specific heat of water. We have the mass of water. And we have the change in temperature of water. The math is already on the next page, so we're going to go kind of back and forth and gander at that. So there's our CM delta T. It gives you lots of joules, and joules would typically be fine, but they want you to convert it to kilojoules. That's dividing by 1,000. Okay, so let's go back. Part B. If you burned 1 mole of propanol, how much heat in kilojoules is released? So, by the way, this Q equals CM delta T that we just did, this is for burning 0.55 grams. So, is 0.55 grams a mole? I doubt it. So, how would you figure that out? So, you'd have to convert this 0.55 grams into moles, okay, and then multiply it by 1 mole. So instead of me doing the math there and getting the calculator out, we'll look at the answers here. So there's our previous answer, 15.2 kilojoules. And I said that 15.2 kilojoules is if you had burned 0.55 grams. So they set up a little conversion here, I guess. And they said let me erase that because that's going to get a little busy. 15.2 kilojoules for every 0.55 grams of propanol burned. And then there's the molar mass of propanol. And then we burned 1 mole. In the question it said how much would you get if you burned 1 mole. So I think most of you would probably get that as a calculator answer. And then let's go back and look at it uses the word 1. So we're not going to use any significant figures with that, but we had the 0.55 measurement. So when we're all done, we need to have 2 significant figures with that. Okay. And then last part of the question. A second student performs the experiment using the same mass of water. So this area up here is identical as it was before. Same initial temperature. However, the student uses an alcohol burner containing the propanol that is contaminated with water. Okay, so the difference in mass of the alcohol burner before and after the combustion in the experiment is also 0.55. So but this time it was contaminated. Would the final temperature of the water in the beaker heated by the alcohol burner in the experiment be greater, less than, or equal to the final temperature of the water in the beaker in the first student's experiment? Well, let's go look at this math here that we've already performed. It's asking what that number would be. For our last question, it was 51.1. This is the same as it was. Specific heat of water is the same. But did we really, actually, this is all about the water, so I don't know if this is going to help us out. Let's actually think about this a little bit differently. So if you burned 0.55 grams, you got a certain amount of energy. But did we really burn 0.55 grams? No, we burned less than 0.55 grams because some of it was water, and water's not going to burn. So if you used less fuel to burn, I think it would be obvious that you would get less energy. And if you got less energy, that change in temperature, well, in this case, that final temperature wouldn't be as significant. Let's see what they provide here. Final temperature measured by the second student would be less. Okay, so that was what I mentioned. The actual mass of propanol combusted would be less. I mentioned that. Of course, it's impossible for you to know how much less because not enough information was provided there. Okay, I'm not really sure that we're going to like this second answer. Combustion of the contaminated sample will also require vaporization of water. Yeah, I don't think anybody's going to really go and try to figure that out as their correct answer. But let's stick with this first part here. Okay. Multi-part phase change question. Calculate the amount of heat needed to heat 180 grams of liquid water from 0 degrees to 182. So you would think that you could just go like this, go Q equals Cm delta T, and go, well, I know the specific heat of water, I know the mass of water, and I know the change in temperature of water. But that is not going to work. And the reason it's not going to work because water only shares these temperatures, everything from 0 degrees Celsius to 100 degrees Celsius. When you're at 182 degrees Celsius, you don't have liquid water anymore. So you can't use this idea. So that's going to require us to go a little back to the drawing board here. So we could go and do that. This would be for H2O liquid. Okay. Then we could do H2O gas, and that's another Q equals Cm delta T. It just is going to require us to use only things that are with gas. And it tells us what the specific heat of the gas is, 1.99. Still the same exact mass of gas. It's just a gas now instead of a liquid. And then the gas got to 182 degrees Celsius, and the gas originated at 100 degrees Celsius. So that's going to work. But here's what we forgot about. There's also energy associated with breaking the bonds to go from a liquid to a gas. And that's going to require us to use the vaporization of water. So, by the way, this answer is going to be in joules. This answer is going to be in joules. But this is in kilojoules. So you're going to have to convert this into kilojoules, so that you could add this answer, and our next answer, add those up. And I didn't put the numbers in here because I'm going to show you the numbers in a second here on the next slide. So we have 1.99, whoops, not 1.99, 40.68 kilojoules per mole I only want the kilojoules in there. I don't want the moles. So I know in 1 mole of water, there is 18 grams of water, and I was provided 180 grams. So that would be able to give us a kilojoules answer. If you add those up, that collectively tells you the amount of energy to make this scenario occur. Now let's take a look at the work there, or the math. So heating the water, that is a Q equals Cm delta T, and I provided that idea above there. So you need 4.18 for the specific heat. All the water mass and the change in temperature is 100 minus 0. Oops. And then heating the liquid to a gas, same idea. That was our new specific heat for gaseous water. Same mass, 180, and now 182 minus 100. So again, we have to use a Q equals Cm delta T for that. It's just that the specific heats are going to be different, and the temperatures are going to be different. So let me change that up. This was this part, sorry. I apologize. So that heating the gas up from 100 to 182 is a Q equals Cm delta T, with the C being the specific heat of gaseous water. And then this part here is that idea right there. So we have the heat of vaporization, and then convert that all the way over to just kilojoules. And that equaled 401 kilojoules. So let's take a look, let's pause for a second and look at these numbers. So if you are just heating liquid water, it requires energy. If you're just heating gaseous water, it requires energy. But if you're breaking the intermolecular forces that hold H2O together with H2O to allow phase change to occur, that's a tremendous amount of energy. So there's way more energy needed for a phase change to break all those intermolecular forces than there is to just heat a substance up. And that's a typical scenario.